then this means multiply 1/4 and 8, and you would get 1/4 times 8. And this is equal to 2 to the power of 2 is equal to 4. So you can see how like this like kind of complicated thing turns into really simple because we're allowed to multiply the exponents. So I guess we can like do some exercises. Maybe like let's do maybe let's do this. Like we do this like in like we try to simplify this and make it extremely like easy instead of like we save the like math stuff like the algebra stuff for the very end and we use exponent rules the whole time. So I'll give you guys some time to do it. Okay, I think Sashi got it, so do you want to explain how you got it?
Yeah, sure.
Okay, thanks.
So first we have 3 to the power of 1/5 times 25. So we'll do 1/5 times 25, and that equals to 25/5. So we get 5. So that's 3 to the power of 5 times 2 to the power of 5. And then you solve for 3 to the power of 5, and I believe that's 243. And then you'll solve for 2 to the power of 5, and that is 32. And then you multiply both the numbers together to get 7,776.
Yeah, great. And I think that we got it too, so good job. And I guess like on the last like one of the last steps here, you can also combine the basis to get 6 to the power 5. And that makes it like sometimes in some cases it makes it easier to solve. Like
You
I
can,
guess one example is like when you do 2 to the power 5 times 5 to the power 5, and when you
mhm,
do it, it becomes a lot easier because you get a 10 to the power 5, and that's just nice. But yeah, thank you, Sasha.
mhm.
Okay, so this is like a pretty chill example. So, in general for math, we have like, we like to substitute like our numbers with variables. So it's like a little more ambiguous, right? And let's do some examples for that. So instead of having 2 and 3, we have like variables. I mean, this is pretty hard, I think. Okay. Okay, let's go over this problem now. So the first step is we know that like okay, this keyboard symbol is basically just like another way to write to the power of 1 over 3. So we can say this is equal to x to the power 4 over 3 times y to the power 2 over 3 to the power of 1 over 3. And make sure it's like you have the parentheses around the entire expression. Okay, and we know that like x and y are different, so there's like really no way we can like put them together even if their bases are the same. So like yeah. So now we just like have to expand it manually. So when we expand it, we get x to the power of okay. So for exponent to the power of exponent, you have multiplication, right? So 4 over 3 times 1 over 3, and then you have 2 over 3 times 1 over 3. And then you have times x to the power of 1 over 6 times y to the power of 5 over 6. And this is just equal to x to the power of 4 over 9 times y to the power of 2 over 9 times x to the power of 1 over 6 times y to the power of 5 over 6. And for when you multiply two exponents together, you have to add the like exponent on the top, right? So that'd be x to the power of 4 over 9 times 1 over 6 times y to the power of 2 over 9. Oops, it's plus 5 over 6. Oh gosh. And this is just equal to x to the power of c. Should be 34 over wait, is it 20? Oh, it's 33 over 54 times y to the power of 57 over 54, right? Okay. And you can simplify this to get x power of 11 over 18 times y to the power of 19 over 18. And I believe this is the best you can do. Okay, cool. So I guess we can do another exercise just to practice. So let's have e to the power of 3 over 4 over q to the power of 2 over 3 times p to the power of 1 over 4, all to the power of -2. Okay, I'll give you guys some time to do it. Okay, so let's go over the question now. So the first thing we do is like, okay, so we see that P and P have the same base, right? So it's like very like natural for us to want to cancel it out. So we do that. Like basically before we expand like an exponent especially, um like the first thing we should do is to see if we can to like simplify the inside enough. So this basically tells us that this is P to the power of P to the power of 3 over 4 times q to the power of negative 2 over 3 times p to the power of negative 1 over 4. Is this like, does that make sense? So we see that p is the same. So since the base is the same, we can like go ahead and add the exponents. And this would be p to the power of 3 over 4 plus negative 1 over 4 times q to the power of negative 2 over 3. And we get p to the power of 2 over 4. Oh yeah, sorry, to the power of negative 2. Times q to the power of negative 2 over 3, all to the power of negative 2. And now that we have something that we can't really simplify further inside the parentheses, we like take all of this to the power of negative 2. So that would be p to the power of p to the power of negative 1 times q to the power of 4 over 3. And when we have a negative, that's not like the nicest thing, so we have q to the power of 4 over 3 over p. So this is a way we can rewrite it. So yeah, those are just like rational exponents in general, and this serves as a foundation for like radical functions. So let's get started into that. So radical function is basically like what we were doing so far. So here is some examples. Like square root of x plus 2. So like these are like pretty much what we've already seen so far, but maybe instead of having x, we have another variable. And what we have here is basically like when we like do operations on them, it's basically what we do above. It's just like following the exponent rules that we already have and like applying on them. And yeah, so I guess like this is a bit different because it's a function. And functions are pretty interesting. So basically a function is like, okay, definition of a function. You can think of it like a machine that takes input and then gives output, right? So what are some functions we can think of? So like maybe f of x is equal to like x squared, and you have like some random input like 1, and then you get 1 out, then you return 1. Or like if you have like x is equal to 7, then you get 49, that's the output. And if we want to look at it rigorously, then the definition is basically like you have two sets. So you have the domain and the range, and the function maps each element from the domain to one unique element of the range. So I guess here's another way we can think about it. So maybe we have like f of x is equal to x squared, right? So like maybe let's just consider like a few points. So we would have like 1, 2, 3, 4. Like let's just look at those points. And then you have 1, 4, 9, 16, right? So we can see how 1 goes to 1, 2 goes to 4, 3 goes to 9, and 4 goes to 6, right? So this is x and this is f of x. And we can see how like it matches perfectly. And then we don't have like, oh, 1 goes to like 4 instead. Like you wouldn't have your machine spitting out 2 elements or 2 outputs if you give it 1 input, because that's not how the machine works. And yeah, so those are domain and ranges. So on this side, it would be the domain. And on the other side, it's a range. So those are just like kind of fancy words. But like, yeah, they're good to know because radical functions actually have pretty interesting domains and ranges. So let's look at them more closely. Let's look at domain first. Okay, so I guess like one common mistake that people tend to use or tend to make is saying that the square root of x squared is equal to x. And we can see that this is not true because, okay, so I guess one of the first things they assume is that the square root of some number is equal to plus or minus, like, right? Or like you can say something like this. So like square root of 4 is equal to plus or minus 2. And that means that there's two solutions to the square root of 4. But this is not true because the square root is actually a function. And we said earlier that every element in the domain should have a unique range, right? So the answer to this square root of 4 should only have one solution, and by convention, it should be 2, right? So there shouldn't be a negative. So that's something to keep in mind. And the reason why this is wrong is because what if you have x is equal to negative 2, right? Then negative 2 to the power of 2 would be 4, and the square root of that would be 2, and that's not equal to 2, negative 2. And because of the domain of radical functions, we have to be pretty careful in solving equations related to that. So first, let's talk about like, yeah, let's talk about that. Okay, wait, first there's like two kinds of radical functions. So you know how like there's like x to the power of like a over b. So the first one is x to the power of a over b, where b is odd. Then in this case, everything is perfectly fine. You can have your domain in like, this is domain by the way. It's just like any real number, and the range is also any real number. Well, I guess it kind of depends on what a is. Um, Otherwise, so it's like a positive real, otherwise, it's any real number. So yeah, this is like the first case. And the second case is if you have x to the power of a plus a over b, and b is odd, and this like a over b is fully simplified. Oops, even. In this case, the domain is equal to the, like, it has to be greater or equal to 0, right? Because like, I guess like we kind of talked about this in the earlier weeks. Like, what if we have like the square root of negative 4? Then because of that, we have to invent like a new thing called I, right? 2i. But in functions, we won't be doing that because, okay, a function should map from like like the function we're like considering right now, it should map from like real numbers to real numbers. And 2 times I is not a real number, so we cannot be considering that. And therefore the domain has to be is greater than or equal to 0. And I guess like another explanation to why we're not allowed to have negative numbers in the domain is because like we can graph the function on a Cartesian plane. And when you do that, you have the x-axis and the y-axis. And if you guys remember from like the complex units lecture, when you have a complex number, then that already has like its own complex plane. So there's no way to graph a complex number without having two axes. But this is not possible because the y-axis only has one, which is itself, right? So like we can't really have complex numbers. So yeah, those are two kinds of radical functions. And oh yeah, the range has to be is also in reals, positive reals. Okay, so with that in mind, we have to be very careful when solving certain types of radical functions. So I guess like we can do some, let's do like let's do something like this. Like, how will we solve that? Like, the first idea would just be to like take the square of both sides. And this will be x plus 2 is equal to 4, right? And this implies x is equal to 2. And everything is perfectly normal. But maybe we have like instead we have square root x plus 2 is equal to negative 2. Then when you square that, you have x plus 2 is equal to 4, and this implies x is equal to 2, which is the same as above, right? But we see that this is not actually possible because we plug it in, you have the square root of 2 plus 2, which is 4. And when you square root that, it's equal to 2, which is not equal to negative 2. So what happened here? The reason why is because, okay, so when you have a polynomial, like you have a polynomial like a to the power of n to the power of like ax to the power of like n, right? Plus b x power of n minus 1 dot dot dot. We learned earlier in the polynomials chapter that this kind of polynomial of degree n has at most n roots. And if you kind of think about like radical functions in this kind of way, then this technically has degree of 1 over 2. Right, so like um if you think about like a polynomial with n root, like degree n, and it has n roots, if you square that polynomial, then the degree would double, right? Because you have x to the power of n times x to the power of n, and that would be x to the power of 2n. So the degree would double. And wouldn't that mean you have 2 to the power 2 times n roots if you square this? And in this case, we are squaring the square root of x plus 2. So we're going from degree 1 over 2 to degree 1. And that means that we're kind of bound to have like some extraneous solutions. Like extra solutions. And this kind of like, this is the reason why we have to plug in our solution at the very end. And this means that you have like x is equal to 2, you plug that back in. So we did 2 plus 2, the square root of that. And yeah, and the reason why this happens, like the reason why we have to do all of this is because the the domain of the function is different. So if you have like x plus 2, we know that this the thing on the inside, it has to be like it has to be positive, right? Because we know that that's the domain of this square root function. But when you square it, there are no more domain restrictions. And when you're changing the domain, you're changing like the amount of solutions you can have. So that's why you have to plug it in. So yeah, let's do like another exercise. Okay, I'll give you guys some time. Okay, so I guess I'm gonna go over this. So you can do something kind of similar to what we did above. So we just square both sides, and this should give 3x plus 1 is equal to, this one is 2 squared. And we're kind of familiar with dealing with that now, so we just expand it. So 3x plus 1 is equal to x squared minus 4x plus 4. And when you move both sides, like when you move things to like one side, then you should get x squared minus 7x plus 3. Is this right? Right, okay. So this means that you would have to factor this. X is equal to 7 plus or minus 49 minus 4 times 3 over 2, which is 7 plus or minus 37 over 2. And yes, this is a bit complicated, but there are two solutions, and we should be like very cautious. So let's kind of think about what happens when we plug in both of them. So 7 minus the cube root of 37, we know that cube root of 37 is about like 6-ish. So the 7 minus 6-ish is about 1, and then over 2, it's like 1 over 2. And then we have on the right hand side 1 over 2 minus 2. That's a negative 3 over 2-ish, right? And this is bad because in our range of the square root function should be all positive reals, and therefore that would not be an answer. So it should just be 7 plus square root 37 over 2. If you do like a sanity check on that one, it's like right. So yeah. Now let's do like a little bit of harder question. Let's look at the square root of x plus 2 plus the square root of x minus 1 is equal to 3. And I know that you can find a way to like guess and check, but let's do this like with the algebra way. Okay, so you don't have that much time, so let's go over this real quick. So I guess like since there's two square roots, that's a little bit like annoying, right? And we do have the square at some point, obviously. So there's two ways we can go about this. So the first way is we just directly square on both sides, and you can try it out for yourself, but I think it's a little bit more difficult and like more algebra, but there's this way, which is what we're gonna do. So we first move one of the exponents to the other side. So we get the square root of x plus 2 is equal to 3 minus the square root of x minus 1. And now we square both sides. So this gives us x plus 2 is equal to 9 minus 6 square root of x minus 1 plus x minus 1. Hopefully this makes sense because you're basically expanding quadratics. And this gives us x cancels out. So if we move the everything else on the other side, we have 8 is equal to 6 is x minus 1. Oops, wait, it should be 6. And can divide by 6, so this is equal to 1. So the square root of x plus 1, x minus 1. And then you square this to get x minus 1 is equal to 1. And therefore, x is equal to 2. You probably would have guessed that, but we know now that this is the only solution, and we plug this back into our equation. So we got the square root of 4 plus the square root of 1 is equal to 3, and that's right. So yeah. Yeah, that's pretty much it for today's class. Thank you guys all for coming. See you guys next week.